I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video where I am showing you the synthesis of this compound, ortho, tertiary, butyl, nitrobenzene. Starting with your benzene ring, we have that tertiary butyl compound, and then ortho to it we have a nitro group. This right here is ortho, tertiary, butyl, benzene. In a shortcut manner, it can be represented as this right here. That's tertiary butyl, and this right here is your nitro. How do we synthesize this from the basic of compounds? I will show you that in this video. The very first item we need to generate is tertiary butyl chloride, and we can write that out for you. Tertiary butyl chloride. We'll generate this from an alkene, a carbon double bond compound with a hydrohalide, which will be HCl. Look, I have this compound right here. I have CH3, CH3, and then look, we'll make sure the valence of carbon is met in all directions. There should be 4 items attached to a carbon, and this looks right. What compound is this? I have 2-methyl propene. Here's 1, here's 2, here's 3. On carbon number 2, I have methyl group, so it's 2-methyl propene. You don't need to say 2-methyl 1-propene. You don't have to put a 1 over because it's understood the numbering for your alkene should be such that the carbon double bond must have the lowest number, so 2-methyl propene. If you were to react this with hydrochloric acid HCl, you can generate tertiary butyl chloride. But there's a possibility something else can generate. Theoretically, possibly, and actuality, you can generate this. And let me show you. You would have CH3, CH3, and then CH2Cl as one possible compound. And then the other possibility would be exactly what you want, tertiary butyl chloride. And this is exactly what it is. You have these methyl groups. You have that carbon and then the chlorine. Tertiary butyl chloride, this is what we need, and this is what we will generate. If you do this reaction here, there's a possibility this can generate, but the reality is this generates. Why does it generate? Because of the Markovnikov rule. And you will probably know this, the Markovnikov rule. What does the Markovnikov rule say? It states that when you're dealing with a hydrohalide, when you have an HX type of compound, a hydrogen and a halogen hydrohalide, the hydrogen will attach to the less substituted carbon. The halogen, the halide, will attach to the more substituted carbon. The reason why this doesn't happen is because this is anti-Markovnikov. This is opposite that rule, where the hydrogen, you see this hydrogen over here, this hydrogen attached to the more substituted carbon, and this chlorine attached to the less substituted carbon. Why is this less substituted? Because this is a primary carbon. This right here is a tertiary carbon. It's the exact opposite of what the rule states. This is what happens is because one of the hydrogens attached here to the less substituted carbon, the chlorine, the halogen group attached to the more substituted carbon. So this is the dominant product, and perhaps the only product based on the Markovnikov rule. Again, the hydrogen of the hydrohalide will attach to the less substituted carbon. The halogen group will attach to the more substituted carbon. And the reason why this is not the dominant product is because of the intermediate carbocation stage. When you're looking at this compound, your carbocation is this, what I'm showing you. You have a primary carbocation developed right over here. My primary carbocation. The primary carbocation is less stable because it is an area of charge deficiency. There's only a single methyl group attached which can donate its electrons, or it can induce its electrons to go over there and fill in this deficiency. It's less stable. This primary carbocation does not like to have a carbocation or a charge deficiency. This item is coming from a tertiary carbocation, and it's more stable, and it is more likely to happen, and it is of lower energy. For this compound, your carbocation looks something like this, and I'll show you. You have a tertiary carbocation, where the carbocation is on a tertiary carbon. You have now 3 methyl groups, 1, 2, 3, which are donating their charge to this deficiency, and it's stabilizing it. Obviously, this is your product which will develop, and that's how we will generate tertiary butyl chloride, which will then attach to your benzene ring. So how does tertiary butyl chloride develop? From your 2-methyl propene reacted with hydrochloric acid in a Markovnikov rule addition reaction, you're gonna generate tertiary butyl chloride. Now I have my tertiary butyl chloride. I'm gonna react it with the benzene ring to generate, in the presence of a Lewis acid, aluminum chloride, in a Friedel-Crafts alkylation reaction to form tertiary butyl benzene, and I'm just representing it as this. And you know this right here is going to be exactly what I'm showing you, a tertiary butyl group but attached to your benzene. and that's what it looks like, but this right is a shortcut symbol for it. So we have our tertiary butyl benzene. Now we have to generate nitrobenzene, and how do we do it? This tertiary butyl group is an ortho para director, meaning on your benzene ring, when you're looking at it, if your item is right over here, it can either add something here in the ortho position or it can add something here in the para position, but it is more likely to add something in the para position, the tertiary butyl, than in the ortho. But we want to have the nitro group attached over here, so how can we guarantee that a nitro group will attach in the ortho position when in reality it would more likely attach to the para position? And you can do so by using a blocking group, and I'll talk about that. When you look at this compound, we're going to block it out. I'm going to block it out with the sulfonic acid. I have H2SO4 in the presence of SO3. When I add it, again it's an ortho para director, more likely a para. It's going to bring here on your benzene ring in the para position a sulfonic acid, SO3H. That's what it is. Now we've blocked this position. It's a reversible blocking, and the procedure is called a reversible sulfonation of benzene. And now when we add the nitro group HNO3 in the presence of H2SO4, it has no choice but to add here in the ortho position. This ortho position are identical. It doesn't matter because you can flip the molecule 180 degrees, and this position is exactly that position. Now when you do it, you have your nitrobenzene developed, but you still have the sulfonic group, but your nitro is in the exact position where you want it, and here's my SO3H. Now we have to somehow get rid of this, and we can. When you do with the presence of water and acid, you can say acid catalyst, and in excess heat you'll burn this off. When you burn this off, you'll have exactly your end result, which is going to be tertiary butyl nitrobenzene, but it'll be ortho tertiary butyl nitrobenzene because this item has now been evaporated away and you've gone to your end result. So this is exactly how we do it. You start here with an alkene, and in the Markovnikov addition reaction you're doing HCl, adding it to it. Through a tertiary carbocation stage, we're adding a hydrohalide. The hydrogen is being added to the primary carbon, and the chlorine, the halide group, is being attached to your tertiary carbon, and you develop tertiary butyl chloride, Friedel-Crafts alkylation, benzene AlCl3, tertiary butyl benzene, and then a sulfonation reaction to develop this a benzene sulfonic acid, but obviously it's tertiary butyl benzene sulfonic acid. Nitrate it, you get your ortho nitro group, burn off the sulfonic acid in a reverse sulfonation reaction, and you get to your end result, and we are done. Thank you for watching.